she does. I yell at her in fourth hour all the time. No, no. I do. And I say,
You have to do homework every day.
we're gonna do day 2 in a second also.
Wait, why are we doing 2 days?
Because maybe if you weren't talking, you would have heard me say it.
I wasn't talking. I heard you say it yesterday. Yeah, oh, maybe we'll double up tomorrow.
Because I already printed the notes out, and we're gonna get through it really quickly. And
Maybe Kimberly and I are.
we can't talk about the quiz because some people haven't taken the quiz. So
Sure to say that.
there we go. That's why. And plus, it's not that exciting stuff. Like it'll be so great. And the great part is you get to do two days of homework.
Who's that great for?
Except I have to take the quiz during work hours.
Oh my gosh, you actually have to do homework at home.
That's never happened before. I just thought I wasn't taking my last Thursday.
So today we're going to talk about the fundamental theorem of calculus, which some is new, but some of it we've been doing. We just didn't say, hey, this is the fundamental. I know, it's really slow. It's not used to get up this early as well. So we're going to do part 1 and part 2 today since, we're awesome. And then we'll do at 5-4 day 3 tomorrow. And I like the why. This is what your book says why you should learn this. The fundamental theorem of calculus is a triumph of mathematical discovery and the key to solving many problems. Right? They're very excited about the fundamental theorem of calculus.
They didn't show an explanation.
I know, right? We wrote this out, or actually I think I printed it out for you the other day. But we say the fundamental theorem of calculus, part 1, is that if f is continuous on the closed interval, and we say that capital F of x is equal to the integral from a to x of f of t. So what I got from this is that if this is the integral, capital F of x represents what? The antiderivative. So like if this was x, capital F of x would be x squared over 2. You with me on that? All right, so just the difference between capital F and lowercase f. And their bounds are from a to x. So notice that a is the lowest part of the bound, but x is just some number in between a and b. You with me on that? We say that it has a derivative at every point in that interval, and that the derivative of this is equal to the derivative of the integral of this. And we talked about this the other day, that that's just going to equal f of x, because the derivative kind of cancels out the integral, but the big part that you got to notice here is this is in terms of t, right? But when you take the derivative with respect to x, this x replaces t. We're going to do some real examples in a minute, but that's kind of what that's all the fundamental theorem part 1 says, which we've talked about already. We've talked about that a derivative and an integral cancel each other out. We just haven't quite talked about that whole replacing t with x thing. So why is this important? This is from your book. I copied and pasted this. It says, it is difficult to overestimate the power of this equation. Because you look at it and you're like, oh, whatever, it's not that big of a deal. But I'm going to read this to you because I'm forcing you to read your book. It says, what does this say? It says that every continuous function f is the derivative of some other function. That's one thing it says. Every continuous function f is the derivative of some other function. Namely, that specific function. What else does it say? It says that every continuous function has an antiderivative. So if your function is continuous, then you can take the antiderivative of it. What else does it say? It says that the processes of integration and differentiation are inverses of one another, which again is not news to us. We've been talking about that since we talked about what integrals are, antiderivatives. If any equation deserves to be called the fundamental theorem of calculus, this equation is surely the one. I didn't write that. Your book did. It's funny. It's a funny book. Like we're really excited about math. But anyway, this says 3 different things. So every continuous function is the derivative of some other function. Every continuous function has an antiderivative, and integrals and derivatives are inverses of each other. That's what. Some people read them. I feel like that's where I failed you in life as a teacher, because like my high school teacher in calculus, he would make us do the lesson before he taught it. So he would be like we would go over homework, and they'd be like, okay, next assignment, read pages, blah, 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 and do these problems. And we would, because I don't make you.
I look back at examples
And then I tried doing my homework and I want to rip my hair out because I'm like, this is so hard, I don't know what I'm doing. And then we talk about it with other classmates, and then the next day he would come in and we would ask questions. We'd be like, I don't understand what this means. But like he was forcing us to learn ourselves as opposed to me just spoon feeding you. Like I feed Nolan.
Yeah.
Where I'm like, here you go.
She's
Let
like
me
getting
put
closer.
these in the knowledge that you need. And then you're gonna go to college and you're gonna say, Dixon, my math teacher is awful, and I'm so glad I saved the notes from your class because they don't teach us anything and they expect us to read the book, and it's really, really hard.
You do know that we would never get any of our homework done. We struggle just already.
That's why you don't turn homework in until later, and so you're always going back and making it up the next night when we go over it and you get your questions answered and you get some of it done. That's how I did calculus when I was in high school because that's what my teacher made me do. And I always say I'm going to force you to do more, and then I just open your mouth for the spoon and applesauce.
I would not say you spoon feed us in 6 months.
Yeah, I definitely.
Here comes the airplane. That's not how I talk to them. So what do we have to do with this first part of the derivative? First part of the fundamental theorem of calculus. And just so you know, fundamental theorem of calculus, we like to abbreviate like that. And on the AP exam, if you ever had to justify your answer using the fundamental theorem of calculus, you could say that, and it's understood among calculus people that FTC means the fundamental theorem of calculus. I know it is, like MVT, mean value theorem. EVT, extreme value theorem. We know these things. But today, what are you doing with this? They're going to ask you to find the derivative of an integral. And the big thing is, let me just rewrite that since I don't have it on here, but you have it on your paper, that if you want to take the derivative of the integral from a to x of f of t dt, the derivative and the integral kind of cancel each other out, and you just replace t with x. Well, some of it, but there's some tricks to it. But no, that is this f, because the derivative cancels out the integral, so you're not actually integrating. Does that make sense? And so on this one, when they say find dy dx, if you're going to take the derivative of this, if it's written like the formula, if it's some number, a could be anything, some number 2x of a function, all you do is you replace t with x. And that is the derivative of that integral. There's no plus c because we're not integrating, we're taking the derivative of it. But obviously they're not going to all be that simple, right? On the AP exam, it's never going to be that simple. Because that's just the direct formula.
So it's the derivative of the integral.
Yes, which is why you're not integrating. That's why you're not actually doing the antiderivative. But if it's not set up this way, you have to think about what's different. So like look at number 2. What's different about number 2 that doesn't fit the actual fundamental theorem of calculus? The x is on bottom and the number's on top. Do we have a way that we can switch it so we can put the x on top and the number on the bottom? Yeah, and you probably would just do this, but I'm going to show my work here. I could write this as negative 6 to x of ln of 1 plus t squared dt. And then, once I have it set up like the fundamental theorem, I can just replace this with x. Yes? But now there's a negative in front of it. So the dy dx, or the derivative of that, is going to be negative ln of 1 plus x squared.
Is this going to be all of our homework tonight?
No. Especially because this is day 1, right? And we're doing day 2 also.
I know, but if we weren't doing day 2.
Pretty much, yes. Which is why we can do double, right?
Would have been nice.
It's Wednesday. Even though yesterday, I kept thinking, yesterday I told for calculus, so on Monday we'll do this. They're like, you mean tomorrow, which is Wednesday? And then I said it again, so Monday, and they're like, it's still Tuesday. I was like, what is wrong with me?
It's funny that we had get up early this morning.
Especially when it's funny.
All right, so now how else can it be more exciting? And this is the kind of stuff that you're going to see on the AP exam. That almost always there's a multiple choice question that asks you to find the derivative of something like this. And what's different about this one from the direct fundamentals here? It's x squared. And so if your function up here is something other than x, you have to kind of think of it as like the chain rule. So let's have vague memories of the chain rule. The chain rule means like when you take the derivative, you then have to take the derivative of the inside function, right? So like if I said find the derivative of sine of x squared, we take the derivative of sine, which is cosine of x squared, but then we have to multiply by the derivative of that, which gives us a 2x out there, right? So if you're taking the derivative of this and you're plugging x in for t, if it's just x, we don't do the chain rule because the derivative of x is just 1. But if it's x squared, when I do the derivative, I'm still just going to replace this with x squared, cosine of x squared, but I have to take the derivative of that as well. And the derivative of x squared would be 2x. And so, you know, you can just leave it like that, but it just bothers me. I like to put the 2x in front. 2x cosine x. And that's really as hard as the first part of the fundamental theorem of calculus gets. Which isn't so bad, right? What about number 4? What can we do with it? Switch it first. So I could say negative 0 to the square root of x of sine of r squared dr. And again, we're going to have to multiply by the derivative of the square root of x, yes? So if you want to kind of do that to the side, you can. I just kind of do it as I go. So I'm going to say the derivative, or dy dx, is equal to negative sine, I'm going to show my work here. So that's going to be the square root of x squared, which is really just going to cancel out, right? And remember that the square root of x is the same as x to the 1/2. So your brain has to switch from integrals to derivatives. What is the derivative of x to the 1/2? Bring down the 1/2, subtract 1. 1/2 x to the negative 1/2. So then, I don't know. I don't care how much you simplify this. Really, in calculus, they don't always care about negative exponents, like moving them down. It's all about matching up with the multiple choice answer. But definitely, I think you should simplify this to x. So you could say like negative sine of x. And since it's a 1/2, you could put a 2 on the bottom. And since I'm going ahead and putting a 2 on the bottom, I'm going to throw the square root down there. But no, you don't have to write it like that. Make it look pretty. So pay attention when it says find the derivative. All right, and sometimes we'll get that later. We should look at some AP questions over this kind of stuff so you can see how it comes into play. Sometimes they give you this and they ask you to find the derivative in part A, and then part B they ask you to actually find another value, which is not derivative. So that's it. Is that the end of your notes today?
Construct a function.
Oh, one more page. I mean, one more. I forgot. Thought I could try to remember myself. Construct a function in this form that satisfies the given conditions, and then I wrote example 4 in your book, because example 4 in your book kind of goes through this in a really long, drawn-out process, maybe making it force read your book again to kind of see where it comes from, maybe. So they tell us that we want to write something like this. Y equals the integral of a to x of f of t dt plus c. What do you think is going to go in for a? How do you know?
Well, I just was guessing.
Are these in terms of x or in terms of y? Are your bounds in terms of x or in terms of y? Always the x-axis, right? Like it's like from 0 to 7 on your x-axis, or from -3 to 4, right? So when they give you a y value, that has nothing to do with your bounds. So even though they give you two numbers there, the y cannot be what goes in for a, because x has to go in. Like an x value has to go in for a. And then Sean's going to have some issues here because we're not plugging 8 in for x, we're plugging 8 in for a, right, Sean?
So we don't even need.
Oh,
to
yeah,
know
this is
zero.
stuff.
It's not really this stuff. It's this stuff here. In the fundamental theorem of calculus, x is always x. But if they give me an x value and they give me a y value, they're kind of giving me a point. Do you agree with me on that? It's kind of like saying they're telling me that y equals 0 when x equals 8. They're giving me the point like 8, 0 is on this graph. Yes? So I could plug in 8 at the bottom here, but in the fundamental theorem, you always leave x up there. So maybe, Sean, we should say x sub 1 here instead of just x, meaning that it represents some x value, not the x that's in the formula. And then we just want to write this in terms of t. So if this was the derivative, and it's in terms of x, do you agree to go back to the integral if we're going backwards? We're just going to change these x's back to t's. So that's just going to become e to the t, tangent t, dt. But it does matter about this plus c of where it started, and that's where the y value comes in. It's really great when y is 0, because that just means that c is 0, and it looks just like all the ones that we've done. But technically speaking, they could give you any number here. If they said y is 3 when x is 3, I don't know why I changed that to 3. If they said y is 3 when x is 8, then it would be like the point 8, 3, and you would have to put a plus 3 here. Because that's the c value that they're giving you. Because when you go backwards, remember, there could be any constant there. But since it's plus 0, I mean, you don't really have to put that there. But I just want you to see in your notes that c is the y value. There's an example 4 in your book. I really recommend that you look at example 4 and kind of read through it, because it talks about this way more in depth, and I feel like maybe makes it make a little more sense than me just telling you exactly what to do on it. Is example 5 like the super important part of this theorem that you're going to see over and over again? No. But it's interesting to look at going backwards. Okay? So part 1 of your homework today is this. So write this down. Or actually, yeah, you need to write this down. I didn't print it off today. And then let's do some more. The good news is this notes are just one page book. It's not even a staple. That's why we can do it all. Let's do not swimming tonight.
We're not swimming tonight?
Like, you don't have swim meet tonight. Like, it would have been bad to double up last night. You can do it all in one or 2 different ones. I don't care. It's on your assignment sheet as day 1 and day 2, so however you want to do it.
When was I supposed to read? I don't have like.
Hold on, is that freezing?
Multiples of 3. Oh, but you could have been reading.
My brain is elsewhere.
Okay. We've been doing the fundamental theorem of calculus part 2 since the last part of section 5.3 when we were doing the area by hand. Because the fundamental theorem of calculus part 2, kids, says that if f is continuous at every point on interval and capital F is the antiderivative, it just says what we've been doing, that the integral from a to b of f of x dx will always equal capital F of b minus capital F of a. Who knew you were doing the fundamental theorem of calculus when you were doing that?
So we're not actually doing anything?
Right, it's just the same stuff, right? That's how we can double up. It's nothing new.
Or we could just.
But I haven't graded the quizzes yet, so we'll see if how we knew it already or not.
We were all pretty confident we got the last one. Right, after we were told that.
After you're complaining about your multiplication, don't say it out loud. Kimberly hasn't taken it.
There's one.
Or Henry. Now, yes, I mean, that's what I said yesterday when I heard he was saying. I was like, oh, now I have to take a quiz. So I always call this a fundamental theorem of calculus. There are many times we'll be looking at AP questions, and I'll say use FTC here because I call this the fundamental theorem of calculus. But it says it also is called the integral evaluation theorem. No one knows that. And again, this is just telling you what it means. Any definite integral of a continuous function can be calculated without taking limits, without using Riemann sums or RAM or rectangles, and without effort, so long as you can find the antiderivative. So this is why, again, this is an important thing we call the fundamental theorem. What?
No effort. It's funny that it says that.
You don't have to make rectangles. You don't have to make an area. You don't have to make a graph. You don't have to do a limit. That's a whole lot of effort.
I hate that.
This is just integrating. So
I'm probably gonna fail it for the transfer.
the big thing is, this means you have to know your derivatives or your integrals, right? Like, so all the trig stuff, the inverse trig stuff, the ln stuff, the e stuff, that's going to show up over and over again. You got to get this stuff down because we're going to end up, it'll get more difficult. Today is supposed to be the without effort part, but it's just plugging numbers in. So evaluate this using an antiderivative or using the fundamental theorem of calculus. So we just do the antiderivative, and I always use the power rule. One of these girls in Calc Lab were telling me that they just always think about, like this, 3x squared, that it would just be x cubed because the derivative of x cubed is 3x squared, which is great. I don't ever, like, I just, without effort, like, rotely do the formula, and I say, oh, this is add 1 to the exponent, divide by that, plus 1x, add 1 to the exponent, divide by that, which is really just b1, right? I'm not really going to do that. But we don't do plus c on this, and this is where I'm really going to be a stickler on notation. When you do the antiderivative, there is no more integral signs because you took the integral. And how we show that we're evaluating this is we draw a straight line and we say we're evaluating it from -1 to 3. And that's how you need to be doing these problems.
So it's not replaceable C.
Yes, because the c gives us just an equation that would work for that problem. This is giving us the area from -1 to 3. So we don't have to worry about some constant out there because this is the actual value that we're looking at of just that area. And then you just plug it in, and this is what people were complaining about. I was making you do this without a calculator. You can do these without a calculator. Rachel was complaining.
I looked at her. I wasn't complaining.
But watch your signs here. Like, this is really just arithmetic, maybe some multiplication, but watch your signs that you're subtracting. It's f of b, which is the top number, minus f of a. So I always just plug this in, 3 to the third plus 3 minus, and then here's where you have options. You can either subtract everything, or you can put parentheses here, and then plug in -1. So that would be like -1 to the third minus 1. Show me something. Because if you make an arithmetic mistake, I need to see that you had the right calculus, and then you just can't add. The good news is on a no calculator part of your test, which I didn't say this yesterday because I wanted to force you to do the arithmetic, but on the AP test, which means on my AP style no calculator test, you don't have to actually do the arithmetic. Like, if you just left your answer like this on a no calculator part of a test, on every response, they give it to you. Does that make sense? Like, as long as you have all numbers, you don't actually have to do the math. Because they don't want you missing it because you add 1 plus 1. Unless it's a no calculator part, you have to work it out. On your homework, work it out because you have a calculator anyway, right? Multiple choice, you got to work it out still to get the number, right? But on free response, no calculator, if it's a bunch of arithmetic and you don't want to work it out, then they don't make you work it out.
So is there a free response with calculator or free response without?
Yes, yes. So we'll just talk about that later, but I'm just letting you know. But this we can do. This is 27 plus 3 minus -1 minus 1, which would be 30 minus -2, which would be 32. Yes? The plan always has been that we finish our new material by spring break, and then after we come back from spring break, we start reviewing. So we do some hardcore 6 weeks of reviewing. But we'll see. We might be in after spring break a little bit, depending on our time schedule. And whatever. But like my plan is we finish chapter 7 before spring break. I give you a take-home test over spring break, as like setting the bar. How do you do on this? And you're supposed to, like, you're gonna do bad on it. Like, that's the plan, because you haven't seen it. And then we keep doing them so you can see yourself improving and that you see the questions more. Well, then you can only do better. But if you get like a 5 on the first one, then I probably because
No
it's hard.
confidence.
It's hard.
You have no confidence.
No, I'm telling you, I've been teaching this a while. It's hard.
You're telling us we're never gonna pass.
No, I know you're gonna pass, but the point is, I set a goal that you show improvement for each test. And the first test, I curve insanely. Like, I don't grade it the way that the actual AP test grades it, because I know that people are gonna do that, because it's hard. But by the third or fourth test that you do, because we're gonna do a lot, you're gonna start seeing the same types of questions. And that's why I spend so much time reviewing, is because it's all about learning the types of questions. And the more you do it, the more you're like, oh, this one's sort of like this. I gotta set up a Riemann sum here, or I gotta do this. And they're tricky, and so you have to practice it. And the first time you do it, it's hard.
Seems like everything you've done is very
Now we're doing integrals. We've been doing integrals since we came back.
Basically the same. It's still the same thing.
It's going backwards. That's all we do. That's calculus. What about this? Do we know how to take the integral of this? How do I take the integral of this? Do we have a quotient rule for integrals? We don't. Which means you have to simplify this so that it's not a fraction, so that it's not division. So you have to do some algebra here. This is where the without effort's kind of a lie. So could I write this as u minus 2 over u to the 1/2? And then you have options. Sean wants to bring it up and make it a negative, which would still be multiplication, and you have to distribute, which is the same thing we're going to get. Can you just, like, put each one over u to the 1/2 as well? Simplify that. It's the same thing, however you want to do it. I don't know. Can we just bring it up? I was just going to subtract, right? Because you have u over this, you could subtract. Okay, let me do it both ways. I was going to do this. Isn't u over... Come on, stupid board. Oh my gosh. Oh my goodness.
It's a new calculus symbol.
Oh my gosh, I hate this board. I'm about to just use the chalkboard.
Not
I mean,
responding.
now you have to gentle with it.
I know, my husband's like, quit clicking things! That's what he always says at home. He's like, it's not helping when you keep clicking. But it makes me feel better. That's what I tell him. Oh, look, it's like, oh, nothing ever happened. It's good.
People are probably the booties well.
Do you agree that that's true? And can't you just subtract exponents when you're dividing? And so that would be 1 minus 1/2 would be u to the 1/2. And you can't subtract that, but you could just bring it up and make that minus 2u to the negative 1/2.
Yeah.
Which is exactly the same thing. That's why I said it's fine what Sean was doing. That just wasn't where I was going. It's just the exact same thing you would get if you wrote this as u minus 2 times u to the negative 1/2. And then you just distribute and add your exponents. So that still would be u to the 1/2 minus 2u to the negative 1/2. Right? It's just however you see it. But you got to simplify it. And this means that with integrals, you're going to get a lot of fractional exponents. And it's okay to leave them as fractional exponents. It's even okay to leave them as negatives. Because if it was multiple choice, I feel like you could match it up. And that's why I say check your odd answers. But you got to simplify it. All of these problems today, you've got to be able to do with the power rule, because that's the only way we have to do integrals. So I'm going to rewrite this from 1 to 4 du. And the power rule is we add 1 and we divide by that. So what do I get if I add 1 to 1/2? 3/2. And if I divide by 3/2, what's that the same as multiplying by? 2/3. So I never write that like dividing by 3/2 because I always know I can flip it up as a reciprocal. And this is why I just automatically do the power rule is for stuff like this. Like there's no way that I think about what would the original function be, right? Like you should just be like add 1 divided by that. Minus 2, if I add 1 to negative 1/2, what do I get? 1/2, and when you divide by 1/2, what's that the same as multiplying by? 2. So you could just write 4 there if you want. I just want you to see where I'm getting these values from. And then I'm going to evaluate that from 1 to 4. From 1 to 4? You'll get there. That's why you do it. And then eventually you'll do it without thinking. And so now we got to plug this in. So I would get 2/3 times 4 to the 3/2 minus, don't grab your calculators yet, 4 times 4 to the 1/2 minus, and I love when it's 1 or 0. That's my favorite bound on an integral because you don't have to think about it so much. So when I plug 1 in there, you get 2/3 times 1 to the 3/2 minus 4 times 1 to the 1/2. And starting with this stuff is where I gave Sarah Woodworth the award in calculus for never knowing what 1 to any power was. Because it's great when it's 1, because it doesn't matter that it's 1 to the 3/2 or 1 to the 1/2 or 1 to the 7/3 or 1 to the negative 7/3. It's just 1, right? So I don't even usually show this. I just write 2/3 minus 4. And yes, you can use your calculator to check these, but I just want to remind you that you could do this without a calculator as well. 4 to the 3/2. How would I do that without a calculator? Yeah, remember that half is a square root? So this is like saying the square root of 4 to the 3rd power. So the square root of 4 is 2, and 2 to the 3rd power is 8. And 4 to the 1/2 is the square root of 4, which is just 2, and 2 times 4 is 8. And that's going to be minus 2/3 plus 4 if I distribute my negative. And honestly, I'm fine, especially on a calculator part, I'm fine with you using a calculator. But like I said, show me something. Show me that you're doing the arithmetic so I can see your work and give you partial credit. And if you want to use a calculator from here, I'm fine with this. What would this be? This would be 16/3 minus 2/3 would be 14/3. Negative 8 plus 4 is minus 4. Two-thirds? Someone do the math on their calculator and tell me if the answer is 2/3. And I cannot stress enough how much you need to use your graphic calculator. I know fractions are easier on your scientific calculator, but start using your graphic calculator because that's all you get on the AP exam. When we take our test in here, that's all I'm going to give you. So learn how to do the problem and the math, enter, and it gives you the fraction. But I'm okay with you using your calculators. Don't use your calculator for like decimals like pi and e. Leave them as pi and e. Like those are better answers. Okay? But that's it. Like that's all day 2. What was I thinking about spending the whole second day on it? But here's your second day homework. I put a little picture of snow to make it better. That's snow days. 27 through 40. All. I think together it's like
What happened to color?
6, 9, 12, 15, 18. It's a lot. 8 and 13. Oh my gosh, you have like 22 problems. 21 problems. 21 problems.
That is a lot of problems. Last time I had that much math homework was like in 5th grade when we had to do 30.
That's not true.